All right, back in business. All right, so we left off looking at the slide where initial rate of reactions measured with several different starting material amounts, and depending on the concentration, we can figure out the order, how they're related. So let's do some practice problems that will, one, help solidify this idea in your mind, and two, get you ready for lab this week. So if you don't have your calculator out, go ahead and get it out because we're going to use it a lot in this class period. All right, so here I have a reaction between ozone and nitrogen dioxide. And I'm told in the word problem that it is first order in both nitrogen dioxide and ozone. So the first question is I want to write a rate equation for this reaction using our standard general form of the rate law. So to write the rate equation for the reaction, I will write rate equals K. And then the concentration, the brackets mean concentration of. So the only thing left for me to do is to figure out what are going to be the exponents next to those brackets. If in the problem it tells me it's first order, what would be the exponent of the concentration of nitrogen dioxide? 1. If it's zero order, then it'll be 0. If it's first order, it'll be 1. And then what about my ozone? If it's also first order, it also gets the exponent of 1.
If you didn't have like where it said like it was first.
Ooh, that's my next example problem. So if it doesn't tell you, my next example problem, it won't tell you, and we'll have to figure it out. Yeah. Very excited. I'm very excited about that problem. So my little daughter says all the time, ooh, and apparently she must get it from me, because I say that a lot. Like, ooh, I'm so excited. And so anytime she's wandering around the house, she'll pick something up and be like, ooh. I'm like, that's right, that's right. All right, so then let's think conceptually. If they are all, if nitrogen, that should be at 2. If nitrogen dioxide is tripled, the concentration is tripled, and we know it's first order, how does the rate of the reaction also increase? It should also triple. All right, if I have ozone and I take the concentration and half it, but it's first order, how does the rate respond? It also halves. Right, so in a first order, whatever you do to the concentration, the rate responds the exact same way. Good there? Okay. Well, let's take a look at now. We'll do a problem where they don't tell us the order of the reaction, but they give us a lot of data that we can determine the order of the reaction from. All right, so here is my table of data that I went into the lab and collected. I have this, I know this is my reaction. I have 2 moles of nitric oxide reacts with oxygen to make 2 moles of nitrogen dioxide. And I went into the lab and I did 3 experiments. All right, here's experiment 1, 2, and 3. All right. So the first thing I want to do is figure out how does the rate change when I change the concentration. All right, so how does the rate change when I change the concentration? So here I have experiment 1, and I have 0.01 molar NO, and I have 0.01 molar oxygen. I want to compare that to another experiment. And I've purposely set this up so that either way you do it, there's only one thing changing, right? So if you are going to do an experiment like you learned in elementary school, you only change one variable at a time, so you know for sure that one variable is making a difference. So if I compare experiment 1 and experiment 2, what happened to my concentration of NO? This right here, what happened to my concentration? Right, it doubled, and what happened to my oxygen concentration? Stayed the same. So I am going to look, if I look at these rates, if I compare those two rates, doubling the concentration of NO will be the only thing that changes the speed of this reaction. Right, does that in words make sense? All right, so change one concentration, hold the other one constant, and look to see how the rate changes. All right, so in my experiment 1 versus experiment 2, we just said that this doubled. What is the relationship between this rate and that rate? Is it the same rate? No. It quadruples, right? It goes up by a factor of 4. So if I double the concentration and the rate quadruples, is that first order? It can't be first order, right? Because they didn't do the same thing. If I doubled it and this squares, right, it's not double, it's quadrupled. It means that this is second order. So it's second order in NO. Let's take a look at the order of the oxygen. So what two experiments should I compare to look at how oxygen makes a difference? 1 and 3. Okay, if we do 1 and 3. If I do 1 and 3, what happens to the concentration of NO? Stays the same, right? I want them to be constant because I want to know about oxygen. What happens to my oxygen concentration? Doubles. What happens to my rate? It also doubles. So if my concentration doubled and my rate doubled, is that 0, 1, or 2 order? First order. We'll do some more practice problems so you can start getting the hang of how to see this. All right, so now, so that's 1, to write the rate equation for this reaction. So we'll write write something like that. What will be the exponent of the NO? 2. Then what's the exponent of my oxygen? Just 1. Yes, ma'am. You don't have to write the 1. I tend to, just to make sure I've finished my thinking process. But if you know for sure, if you've written it down someplace else, then you know to write it over there. All right, so then I want to calculate the rate constant. Which of these variables over here is the rate constant? K. So I want to figure out K. Which experiment would you like to use to solve for K? Doesn't make any difference to me. Number 1, good choice, because that's what I have in my notes. All right, so the rate is over here. All right, let's see what that turns out to be. We'll deal with units in a second. Let's just get the numerical part of it right. Then we'll talk about units. How many significant figures do I get to have in my final answer? 2. Either 25 or 2.5 times 10 to the first, both would be fine. If I get something like that. Okay, let's look at these crazy units. What are my units over here? I got moles per liter squared times moles per liter. So what are my units on the right side? Moles per liter cubed. And over here I had moles per liter second. So for those to cancel out, this will cancel out with that, and that will that. And you get 2 and 2. So you'll end up with something crazy like that.
So it depends on your orders, what you need.
Yeah. So when you're doing these problems on mastering and ask for the units, the order is going to affect the units. Did I have it upside down? I think I have it upside down. That should be liters, and that should be moles. There we go. There we go. But yeah, so the units will depend on what the order is. So there is no good rule as to the units of K are always something something. They're going to depend on, in this case, what's the overall order for this one? 3. The overall order is 3 because I have 2 plus 1. So the overall order, sometimes there'll be a question like this. That's what the overall order of the reaction is. It's third order overall. All right, let's see here. I'm going to leave you guys to do number 4 on your own. It's just plugging it back in. So instead of, now that you know K, use K to find a new rate. So you guys can do that as a practice problem for later. So do 4 on your own. We'll do another problem like this. Actually, let me do an easier one. That one's tricky. Let me do an easier one first. All right, so let's do a warm-up, second warm-up. All right, let's say I did this reaction. And I collected this set of data. And this time I did 4 trials. I want to figure out what is the rate law for this reaction. So again, we got to look at the 2 different concentrations, hold one constant, change one, see what the rate is, and then do the reverse. So Let's take a look at, we'll do A first, all right? So we'll do A first. What two experiments would you like to look at to see how A changes? 1 and 2, okay. So if we do 1 and 2, what happens to the concentration of A between experiments 1 and 2? Doubles. This doesn't change, that's good. What happened to my rate? Pretty close to doubles, right?
So it doesn't matter, it doesn't matter.
Yeah, experimental data is going to be a little funky, so it's going to be a nearest whole number, either double, triple, whatever. Okay. All right, so if the concentration doubled and my rate doubled, what order is that? First order, okay. Let's look at B. What two experiments would you like to look at to compare B? Probably 2 and 3 are the easiest, yeah. Okay, so what happens to my concentration of B between 2 and 3? All right, that doubles. What happens to my what happens to my rate? Quadruples, goes up by a factor of 4, okay. So if that doubles and that quadruples, what order is it in B? Second. How do I feel about that? Pretty confident? It's kind of like a little logic puzzle, seeing who changes and how the change affects the rate. So then, as always, the second part to these is, what is K? And we'll just pick experiment number 1. Everybody, something similar to that? How do you what? Let me get myself another clean piece of paper. So here I had moles per liter seconds, and then on this side I have moles cubed over liters cubed. So because I'm doing division, I'm dividing this side over this side. So then I end up with this side being just some funky algebra division rearrangement. All right, yeah, Paul.
So for the determine the rate order, I don't understand. Are you taking like 4 divided by 2 to get the second order for B?
4 divided by
2 divided by 2 to get the first order for A?
Yeah,
Oh, okay.
that's it.
How is the other way to do that?
Just know that if it's the same as first order, if it doubles, if you double that and it quadruples, that's second order. And if that doubles and the rate doesn't change, then it's 0. There's only ever going to be 3 choices: 0, 1, and 2. So 0, the rate doesn't change regardless of what you do. First order, if you double it, it doubles. If you triple it, triples. In second order, if you double and quadruples, then it's second order.
Okay, great.
So if it were 0, like 1 and 2 would have stayed.
The rate would have been constant. In fact, the rate would have been the same for every single one of these, because the concentration of A apparently is making no difference to how fast it goes.
And so the overall rate would be 3.
Yeah. All right, you ready for the challenge problem? Okay. So here I have my experimental data. I went into the lab and I collected this very fancy data set for my very boring reaction, A plus B goes to C, which is my reaction for everything. So I went ahead and I collected some data. What is a problem you see with the data I collected? I didn't pick a good set of concentrations, right? So I can figure out, we can figure out the order of A, right? Because if I do this set of runs, right, B is constant, what happens to the concentration of A? Right, that doubled. And then what happened to my rate? Quadrupled. So what is the order of A? Second. Can I do anything like that for B? No. I wasn't paying real great attention when I decided to pick out what runs to do. And I didn't hold A constant for any of my 3 runs. Don't you worry. We can solve it. We can solve it. So right now we're at this point. Right, that's where we're left at. Well, lucky for you, last week in lab, you did all this base 10 natural log stuff. These are just review problems in case you forgot. You can go back and do these. Important properties of natural logs and base 10 logs in case you forgot. Those fun facts. Let's go ahead and put those into practice. Let's do some base 10 log stuff. Which, if you're doing lab this week, this is the problem that you use in the pre-lab. Something similar to this. All right, so here we're at. We're at the rate equals equilibrium constant, A squared, B to the power of X. All right, from our experimental data, we definitely know the relationship between 2 different sets of runs, right? I definitely know what the rate is between 2 runs, and I know all the concentrations. What do we know about the rate constant for any one of these runs? Is the rate constant going to change, or is the rate constant going to be a constant? It should be a constant. That is super helpful, because now I can say this. Right, so the ratio between those 2 is going to be solvable. What happens to these 2 K constants in my fraction here? They cancel out, okay? So now I'm left with the rate of 1 equals the concentration of A squared B to the X over the rate of a second reaction, A squared B to the X. So I went ahead and I picked, I guess we can all pick together. We want 2 runs where the concentration of B changes because we're interested in B. So which 2 runs should I pick to compare? 2 and 3 is fine. So, actually, let's do this. I'll just go ahead and write the rate. So rate of 2. I'm going to leave off all the units for now because it just take up a lot of space. We'll go back and we'll figure out the units later. All right, concentration of A in that one was 0.2 squared, 0.1 to the x. All right, so that's just plugging in the data from the table. Look how handy that is. I'm down to just one variable that I can solve for. Oh, I'm getting excited, right? Solving for x. All right, so let's go ahead and let's solve this side. Figure out what that is numerically. 9.00. I'm going to also keep a lot of significant figures till the end, so I do the rounding at the end. All right, what's something I can do on this side of the equation to simplify, numerically simplify it? Go ahead and do this part of the math. Do the 0.2 squared divided by 0.4 squared. All right, so now I've gotten all the numbers mostly all sorted out. I'm going to do one more simplification step. I'm going to get all my numbers on the left and leave all the things with the x on the right. So far, so good? I haven't made any math errors. I didn't do this. I picked 2 different ones in my notes, so doing along with everybody else. All right. We can now simplify that using our knowledge of things we can do with exponents. We can go ahead and divide these 2 numbers and leave it to the power of x. All right, we can do the division, and now it's just 0.5 to the power of x. Using the fun fact using this fun fact about logs, if I take the log of a value raised to the power of x, it is equivalent to x times log times that value. Hopefully you guys did that in your worksheets a few times. Good. So, next step will be to take the log of both sides of the equation. And look at that, we're like one step away from solving it. Look how easy that was, straightforward, just plugging it in, doing some rearranging. Hopefully everybody's excited as I am. We're getting close. All right, so now we can just go ahead and solve that. So log of 0.125 divided by log of 0.5. Everybody else get 3. Awesome. So now I want to finish writing my rate equation. It's not terrible, right? Not terrible. Mostly just some algebra. Moving things around. Tedious. I didn't say it wasn't tedious, but yeah.
On the test, you want us to solve it like, will we get points count off if we don't solve it like that? Or are you just looking for the right answer?
I'm just looking for the right answer. The more work you show, though, if your right answer is not right, then it's hard for me to give you any kind of extra credit. So my suggestion is always write down all your steps as you're going through them. That way, in case somehow we get astray I can say, oh, you forgot a plus sign or something. So the more work you show, the better on these kind of problems. What's the overall rate for this equation? 5. Mm-hmm. All right, that's the trickiest problem you can possibly have with this kind of experiment. So if you feel fairly confident about this, then you're good on all the other ones. Because most of the ones that you're going to see, you can just see by sight. You can say, oh, doubles, doubles, or doubles, quadruples. All right. Let's talk about concentration and time and how they're related. All right, so concentration and time. It is useful as a scientist to know how long a reaction is going to need to take to get to a concentration you can measure, right? Do you need to let the reaction go for an hour, or do you need to let it go 24 hours, right? That's a big use of your time. You need to know how long it's going to take. And then you also want to know, well, let's say I stop it after 6 hours. Will there be concentrations that I can measure of both reactant and product? So we're interested in how far does a reaction get in a given amount of time. So it's not possible to answer these questions using just the rate law. Right, so the rate law will tell you, given these concentrations, we know how fast the reaction's going, but it doesn't tell you after 6 hours how much is there. We don't have that information from the rate law. Don't panic. Don't panic. We can determine a time required to reach a given concentration. You can solve it using calculus. Woo! How many people have taken calculus? Awesome, awesome. For those who haven't taken calculus yet, you're in for a treat. All right, so let's say I have this reaction, my very super simple reaction. A goes to B. All right, all the A makes all the B. I can write my rate law for it. But it still doesn't answer the question, after 6 hours, how much A is left? Or after 6 hours, how much of B has been made? It doesn't answer that question. It just says how fast the reaction is proceeding. So what we need to do is find the integrated rate equation. This will be very baby, very baby. All right. So remembering from Wednesday, if I wanted to write the rate equation, not the rate law, the rate equation, is the A appearing or disappearing? Disappearing, so does it get a positive or negative sign? Negative, okay. Right, that would be true. If I was writing a rate equation for it, that the disappearance of A over time has some rate. So that also has to be true to this. Right, so now I've related some sort of change in time to this rate constant. For those who have taken calculus, big D, right, big delta is big change in. Well, if I want to do just a little change in, what letter does that get? Little d. Little d. Okay, what do you do when you want to get rid of those little d's in calculus? You're going to integrate. We're not actually going to do it. I'm just going to show you this next step, and then we're going to skip to the end. My integral signs look kind of crazy. Right, that's how you'd solve it. If you're in calculus and you want to know the change in, you'd integrate over the area that's changing in or over the time that's changing in. So we're going to skip to the end. If you've had calculus, at this point it's just algebra. You're just rearranging so that all the a's are on one side and all the t's are on the other equation. And you're just integrating over a or t. If you'd like me to work it through, come by my office. I'd be more than happy to walk you through how to solve for that. And then we can do the other rate laws too. We can do 0, we can do 2. Anytime. No one ever comes by and asks, hey, let's integrate. So, a few steps later, we're going to get this. Go ahead and box that. We're going to use that a lot.
Do we need to know how to integrate?
Now, I would love for you to know how to integrate, but you do not have to be able to work through it. Just know that the integrated first law, or integrated rate equation for first order reactions, is this.
This is a constant equation, I guess.
For all first order equations, this is the integrated rate law. Yes, ma'am.
It's a little zero.
It is. It's a little zero. I'll work through what the definitions are here in a second. Let me define them over here. All right, so there's going to be, K is our same K that we've had before a bunch of times. A, the A that's over here on the left side of the equation, is the concentration at some given time, 6 hours in or 20 minutes, whatever time period you're interested in. T is that time period, so they should be related somehow. You pick the same T to figure out that concentration. Then A0 is how much you put in there to begin with, the concentration before the reaction started. So if you know the concentration before it started, and you know how much time has elapsed, we should be able to figure out how much is left in there. It's all sorts of useful. I don't know why you would know the concentration after some time in the initial and not K. But let's say you did. You can figure out K. That's good. This is more likely. You know the rate constant and you know how much you put in there. And you want to know after 6 hours how much is left. Or if you know K and you know time, you could figure out the ratio of starting material to ending material. Those are all ways we could use this. Ooh, fun fact before I get too distracted. Because next we're going to graph. Oh, I'm so excited. Graph this. This negative sign here, that negative right there, what would you predict? After 6 hours, should there be more or less starting material? There should be. That's what the negative sign shows you. That the concentration of A has to be less than the concentration of A0. You have to have less on this side than when you started. So that's what that negative sign's in there for. That's why it's critical that you don't lose it. It'll mess you up. All right. Bless you. I didn't leave myself nearly enough space to make this graph I want to make. I'm very excited. All right, so here's my equation again. right? Here's the same equation I just wrote over there. All right. If I want to graph a line, what is the equation of a line? Y equals mx plus b. Y equals mx plus b. If I map those on top of each other, what then is going to be the x-axis for my graph? Time. What then should be the y-axis of my graph? This guy over here. If it is m is the slope, and if m, the slope is equal to negative k, which direction is my slope going? Going this way or that way? It needs to be going down, okay? And then, what is my y-intercept? Which makes sense, right? Because the highest point of this should be our original concentration. And as the reaction proceeds, the concentration will go down with increasing time. So there's going to be some questions probably on the mastering, I think, for Wednesday. If you see a graph like this, you know it's this equation. And you should be able to like plug things in from the graph. Points from the graph. All right, so let's do a practice problem using our first order reaction information. Let's see if I can find it. Nope. Sorry. Apparently, I didn't put it in my notes this year. I want to do it. All right, so I know the rate constant for this equation. I know my initial concentration. I want to know how long is it going to take until I get to a new concentration of A. It is. Apparently I'm not very good in focus today. All right, so this value is over here. So at this point, we should be able to just plug some things in. So far, I haven't missed anything yet. Okay, what's my next step to try and get TL by itself? Yeah, get these moles per liters all on the same side. Or something ballpark like that, depending on how much you rounded. Ballpark, okay. All right, how do we feel about that? That's just gonna be some practice figuring out, depending on your calculator, either you need to press natural log, right, then the value, or value, then natural log. Just gonna take some practice to make sure you get it plugged in correctly. 'Cause that's gonna be the, if you're gonna make a mistake on these, it's not probably gonna be the algebra, it's gonna be plugging into your calculator incorrectly. All right, we'll stop there. We'll do some other reactions and then half-lives. We will do some more good stuff.